Thank you very much for the introduction, and thanks for the invitation to this meeting. It's really amazing to be here. My talk today will be about neuromorphic computing, attractor dynamics, and the neuronal basis of autonomous behavior. I will mostly focus on neuromorphic computing because I think that's probably the most interesting topic to the audience here. I will only briefly touch on attractor dynamics because many of you probably know, and this has been already said a lot about why these attractor dynamics are important for autonomous behavior. And I will mostly, I will emphasize the autonomous behavior as the first thing that I will touch upon. Let's see, I'm from Intel Labs, so I have to show you this slide with some legal information. You can read it later offline in my slides if you're interested. All right, so autonomous behavior. So the big question that I would like to put in the room is, where is embodied AI? On the first day of the conference, I was really happy in the introductory word of Joe Payton to hear him cite Rodney Brooks with his "elephants don't play chess." Because indeed they don't. And let's be honest, many of the humans also don't. And even those who do, they don't do it most of their time. Most of their time, they do other stuff. Like they walk around, they walk the stairs, they walk down the hill, they make themselves coffee and they drink it, and they grab tons of things. They clean up their children's room, and some of them do dishes. They do a lot of stuff. So a lot of what we as humans do is about moving ourselves and moving things around there. And in fact, there's an opinion that the whole neural system and all the brains, they have evolved to move. If you don't move, you don't really need a brain. So this moving around and communicating with the body is an important part of the brains are doing. So I would like to put this elephant in the room to stay with the elephants for a while here, that where is all that movement, both in AI and in the neuroscience. It seems to be really difficult to embrace the neuronal systems as controlling movement, and movement and behavior generation as being important part of the story. So what are the challenges of AI today in robotics, in the field where we need to move things around? And also, as we have heard on the very first day, perception seems to be a bottleneck, which must be a good news, because in AI, we kind of know how to do perception, right? Image processing is almost solved, and vision and perception is the thing that AI has solved. But there seem to be a couple components missing to really make it work in real-world systems that move around. And what is missing is a lot, and there are some hard problems that seem to be missing. Memory is the first one, and then also as hard as anything else. There are also some hard AI problems that probably need to be solved, like symbol grounding, compositionality, how do I build the systems that scale up? Intentionality, how can I direct my thoughts and inner states on some things out there in the world. Also flexibility, ability to solve many different tasks and switch between them flexibly. Adaptation and self-calibration are important. Robotic systems, they change all the time slightly, so you have to recalibrate them regularly. And also autonomous learning at different time scales. So the system needs to learn after deployment many different things, somehow discovering when to learn and what to learn. And last but not least, efficiency. If you want to have a robotic system controlled by your AI system, yeah, something is wrong. Now it should be less annoying. Right, so time and energy is also important, because robotic systems, they cannot always be plugged into the world, and you also need your solution at millisecond time scale at most, really quickly. So I do believe that neuromorphic computing and attractor dynamics are at least part of the answer of how can we make our robots not just do the math behind playing chess, but actually move the pieces on the board in the end. All right, so I'll start with neuromorphic computing. And the first thing I'll do is just place neuromorphic computing on this timeline of the history of AI, so that we know where it starts and doesn't end yet for sure. So the history of AI has these two components, right? One of them is the classical AI, symbol processing, starting with the Turing questioning, can machines think? And of course, answering it positively, and probably ending at Blue Brain winning Garry Kasparov in chess. And then all this history, with overpromising, that not quite delivering in between, but in fact, serving a lot our society today, because all the software, all these digitalization systems that we have today, they were driven by this wish to build smarter and smarter systems that can solve problems like we humans do. On the other side, we have a history of neural networks, right, that unfolded in parallel, also starting approximately at the same time, and definitely not ending now, also with its ups and downs and neuronal winters a couple times. arriving today in the GPU era, where we have these very large models that very successfully solve image processing tasks better than humans do. So kind of answering to that promise that by 2001 we'll have systems that do something at least better than humans do. So the neuromorphic computing comes into play relatively late in this story, around like mid-80s. It comes in Kava Mead's lab in Caltech, and it started with the sensor. So not with the processor with the brain, but with the sensor, with the event-based or retina-like camera developed by Misha Mahovald. And then from there on, so people started with a sensor, but then they started building little pieces of cortex in silico, in hardware, using analog electronics in the beginning, in the spirit of the 80s, but then switching more and more to digital ones. And I have put some examples, so if you don't see your favorite neuromorphic chip here, don't be offended, but just the most prominent examples. Rolls and Dynam from Zurich, this is the mixed signal analog chip, Brain Scales, Neurogrid, Spinnaker, True North, and now the most latest ones are Loihi chips from Intel. I have highlighted the hardware developments that were driving AI revolution and AI evolution so far. Moore's law as the first driving force, just our CPUs getting faster and faster, the GPUs that gave rise to neuronal networks that we know today. And neuromorphic hardware is just another type of hardware, and it's another in that sense. It's fundamentally different type of hardware that hopefully will give rise to new architectures and new algorithms that will solve new types of problems. So I think that's that fundamental of a shift in hardware development. So what do people call neuromorphic hardware? There are different designs out there. Some come from academic labs, some from big companies like Intel, some from startups. And different people call very different designs neuromorphic hardware. And one of the biggest differences is whether we use conventional digital electronics like Intel does, or mixed signal electronics with analog and digital, and that's more exotic and has some good properties but also some challenges, or new materials. So you might have heard about memristive technology and the neuromorphic chips that use these new materials where in a single device you can have a little memory cell that acts like a synapse between neurons. And they are on different technology readiness level. So if you hear neuromorphic computing, you shouldn't think of something super exotic where you have 8 neurons and it's like quantum computing, something we will see on the market in 10 years. There are also systems that use today's technology, and it can be on the market very quickly. So what unites all this system? What is a neuromorphic chip, and how is it different from other neuronal network accelerators out there, VPU or TPU? So I highlight 3 main differences, usually. The first is the neuronal model used, and the neuronal model is not just a ReLU or some other nonlinearity that you probably know from artificial neural networks. It's a spiking neuronal model. The most typical is a leaky integrate and fire. What does it mean? So leaky means that you have some exponential decay over time, meaning that your neuron now has a state. So it has a state and it evolves over time. It's not that the neuron is just a number that is updated with every input. It's a variable that is maintained. And even without input, it will have some temporal development. Typically just decay, leaky, integrate, and fire. And the second kind of particularity of this model is that it's spiking, meaning that the neurons send each other binary events if their internal variable reaches some threshold, similar to biological neurons, or a simple model of those. So the neurons integrate inputs that come in their internal variable. If this internal variable reaches a threshold, then they will communicate a discrete binary event to everyone connected to them. So instead of exchanging values and numbers with some clocked time, they will exchange these signals that my threshold has been reached asynchronously over time. So it's quite different representation and sampling of signals and information. So instead of matrices of numbers that you have to analyze, you have the special temporal patterns that unfold. The second difference is the network topology. And the network topology is just free. It's left free to the designer of the neuronal network. You can build a feed-forward all-to-all connected network. You can build a convolutional neural network. But you could also build some other structure. You could build a little neuronal oscillator, like a CPG. Or you could build like a little recurrent network or module, and then interconnect many such modules in a larger system. So the space of algorithms that open up here is quite large. So you can think of any graph-like looking structure that could solve your task. And the final difference is learning. Learning is, of course, an important property, right, of neural networks. We do neural networks because we want our systems to learn and not program them. So neuromorphic hardware supports learning that is biologically inspired. So it's the learning that we know from biological systems, and that's typically some kind of Hebbian learning, spike time-dependent plasticity of some kind. So what does it mean? It means that each synapse can update its value anytime when the network is computing something based on activity of the pre- and postsynaptic neuron, of the two neurons that the synapse connects, and nothing else in the network. So it's not informed about the state of other weights in the network. It's not so easy to renormalize the whole system. So there are some constraints that locality of this learning rule imposes, but that's what we know from biology. Biological systems somehow manage to learn all kind of amazing things with these learning rules, so why not try to do that in artificial systems themselves? Yeah, so the local learning rules. In Intel's realization, this hardware looks something like this. So it's a large mesh of little cores. Each core can compute 1,000 such spiking neurons. On the chip, you would have 128 such cores. So you have approximately 100,000 neurons on one chip, and now you can stack these chips in a larger system. It supports some level of fan-out, not all-to-all connectivity. So you have some limitations to how many other neurons you can talk. Complex network topology is scalable on-chip learning, so every synapse can change anytime. It won't draw additional energy from you, but you have to define that learning rule. Right, so a little animation just to give you a feeling how it works. So in any core, any neuron can emit a spike. The spike will be communicated to all other neurons with which this one connected, and then the whole mesh is just optimized for this spike-based communication. And then the whole system synchronizes once in a while to make sure that one core doesn't go ahead in time compared to the other core. So you have this concept of time step, and the physical duration of the time step might vary because in some time step you might have to compute a bit more. Okay, there are a couple slides with a different scheme. This is from our recent announcement when we announced Loihi 2, the next generation of our chip. With the first generation, we've discovered inefficient neural model flexibility. So only having the sleek integrate and fire neuron is nice, but not enough for many people. Binary spikes sometimes cause precision. So there is some limitation in that. And in electronics, we don't have to stick to binary spikes. And there was limited support for some learning algorithms. So we wanted to get rid of that. And then some efficiency. This is just some hardware inefficiencies that were there. So in the shiny new Loihi 2 chip, we got rid of these limitations. So now we have programmable neurons. We have spikes that can carry value, a couple bits or 8, 16 bits of value with them. And we have enhanced learning rule with 3 fractal learning rules. And also just in terms of hardware, it's faster, bigger, better. Okay, so that's the hardware. Now the question, we have this piece of hardware. It looks like Cortex, it behaves like Cortex. How can we make it do something as useful as what Cortex does? How can we build some embodied AIs, all those elephants that don't play chess but do other useful things in neuromorphic hardware? And I'll give you one example of how that can be done, but first like a little kind of background slide. So what does it entail to build a system like that? If we have our robot, the robot usually has many different sensors. It has an image sensor, but it also has maybe acoustic sensor, has some tactile sensor, has some proprioceptive feedback. All these sensors, they deliver signals to your system at different time scales. Some come 30 times per second, some comes 1,000 times per second. And what our neuronal system in the middle needs to do in order to control all kind of movements that this robot might need to do is create some kind of a representation of its immediate environment around it that is somehow stable and sustained and can be updated with this new sensory information that comes at some times that you might not know in advance. And typically, if you do that, you want to create multiple feedback loops because your motor systems, they also work at different time scales. And they might require sensory input at different time scales. So it's very much following Rodney Brooks' actually ideas of this architecture, modular control architecture, where you create little feedback loops for different tasks that your robot needs to do. Avoid obstacles, go to targets, move your head or move your hand. And then we need to create a hierarchy of maps for sensor fusion, but also just for planning. And you need this hierarchy because you might need very coarse planning for long scales, but very precise planning for your next second of your movement. And you need this memory information on different spatial and temporal timescales. So this is kind of a system that we want to build. And we believe that particular type of networks, attractor networks, are well suited to build that kind of architectures. What are attractor networks? Just three plots to make the point. So as you might know, attractor in a dynamical system is a state that is stabilized. So you create forces and interactions in your dynamical system so that if there's some perturbation and tries to bring your system out of the state, it will be dragged back. You just stay there. In neuronal network terms, it means that you have some population of neurons and you wire up this population stimulation in such a way that it creates these stable activation states. The typical one would be some bump of activity, a peak of activity that is stabilized. If you input fluctuates and try to drag this bump, destroy this bump, it will be stabilized, it will stay there. And this is an important property, to bridge those time scales. Because now if you're in a stable state, you will stay there until something will destabilize this state. And that allows you to bridge the neuronal time scale with the behavioral time scale, which can be on seconds and minutes. So what we can do in neuromorphic hardware, using the software framework that we also have released recently, is to build building blocks. Each of them is a little attractor networks, and use them like Lego building blocks to build architectures that can now solve different tasks. And I'll give one example of that in the remaining 5 minutes of my talk. But first, what do these attractor networks enable? I won't go into detail, I will just list. So they enable memory on different time scales, because a tractor can stay as long as you want. It can stay 100 milliseconds, it can stay 5 minutes. If that attractor, find my key, you will stay in that attractor and will look for your keys until you find them. Or, finish the grant today. It does attentional filtering, because it filters out everything that is not supporting this attractor. So it helps you to kind of select where to direct your attention. It creates stable states that are required to control movement. So to control movement, your neuronal state needs to stay in the state that represents the goal of your movement until I'm there. You cannot just create the state A and then move to state B and then move to state C, because your motor system won't catch up so quickly. And it also allows you to build transparent neuronal architectures, because remember, you have these Lego building blocks, and you build your architecture out of those. And learning will be part of it. Here and there, you will have some mappings, some simple one layer of synapses that will be plastic and that you can use to learn something. But large portions of the architectures, you just know exactly what these parts are supposed to be doing, and it's easier to debug such an architecture. One example is object learning. Why object learning? Because object learning is what AI is doing really, really well. If I want to do object learning with my robot, the task is slightly different than the typical image recognition task. Because my robot, let's assume it's a robot in my home environment, and I wanted to recognize 3 objects, my favorite coffee cup, and my phone, and the bottle of water. And they are this particular coffee cup, bottle of water, and phone. I don't care if it can recognize all the cars and pencils and then whatever in this world. I only care about these 3 objects. So you can imagine that the architecture that will be able to learn this object is quite different than the one that can recognize any cat or any dog or any other class out there. And the architecture that we have built to do that looks something like this. So you do have some pre-processing that is some more or less deep feature extraction that will allow us to create some compact representation of our objects. Important thing that I want to recognize my object under different views, because I might see it on very different views and different backgrounds. So I might want to take care of that. And I want to recognize a couple objects. The important part of this architecture, however, is this little network of nodes. We call it neuronal state machine. And this neuronal state machine detects different states in which this system can be. And it can be, for instance, in the state, I see an object, and I don't recognize it. So it's an object that I don't know. That's a state that will trigger certain behavior. I will ask the user, what is this? Give me a label for it. Then I hear a label. I will be in another state. I hear a label. I have heard this label before. I must know this object, but I don't recognize it. So it means I have to update my representation for that object. And it will trigger certain learning and update processes. I could be in a state, I hear a label. I have never heard it before. It's a new label. It's a new object that will trigger other processes. I will recruit some new neurons that will learn representation for this particular object. If I see an object that I've seen before, but I don't recognize it now, I will assume it's in some new view, and I will probably recruit new neurons, the new neuron that will learn a new view for this object. So over time, interacting with the user, observing these different objects, I will learn representation for different objects, and will be ready to update it any time, because I have this system that monitors different states in which my system can find itself. So we have shown on a couple simple examples that you can do that, and you can kind of autonomously decide how many neurons you use to sample different objects. If you have a ball, then probably 1 neuron is enough to represent its roundness. And if I have a bottle, then maybe 2 or 3 are enough. And for some complicated object, I might need 8 or even more if it would be a more complex setting. And then in terms of continual learning paradigm, it learns continuously as other continual learning paradigms would learn. We really show it in this interactive scenario, so we don't have the full batch from the beginning. We pretend we don't know it. The important thing is here, so even on this prototype Loihi chip that uses today's electronics, we achieve like 300 better power consumption, both for training and inference, because training and inference uses exactly the same dynamics. There's basically no difference. This learning dynamics just runs all the time in parallel. And it's also a little bit faster, but it was not our goal to have a very fast architecture. Now, this architecture is not the end of the story, because now in order to actually use this architecture in this embodied autonomous setting, we need more bells and whistles around. For instance, we want our architecture to be fast and lightweight. So we don't want to process the whole visual field of view of the robot all the time. We focus on a little region of interest in the center of visual field, like a fovea. And now the task will be to move this fovea around to interesting parts. So what we have is an attention dynamics that will tell us where interesting things are in the environment. And we have a little behavioral organization system, again, a state machine, that will make the robot look at an interesting object, bring it in the center of visual field, so that now I can try to recognize it. If I don't recognize it, I will trigger learn behavior. Now ask for the label, try to learn. If I recognize it, I will look for at another object. And then while doing that, I will also try to build a spatial map of the environment. So remember where the objects were, could be useful if I don't see them at some point. So as you see, so I build a neuronal architecture. Every module here is a little neuronal network, but its structure is very different. There is some deep network here, but there is also these neuronal state machines and this SLAM network for simultaneous localization and network. And in neuromorphic hardware, I can just build it like I program a computer in a way, but I program a neuronal network that can then run very efficiently. I will skip the SLAM architecture. You can just believe me, following the neuroscience insights, how navigation circuits in hippocampus and entorhinal cortex and other structures in brains work. We can build an architecture that does localization, odometry, and mapping on chip. I will show this plot briefly. It's our benchmarking plot that shows different algorithms, how well they run on Loihi versus other hardware systems, so CPU, GPU, Movidius, or TrueNorth architecture, in terms of energy, so how much less energy they consume and how fast they work. So just two interesting points. In this corner, where Loihi is not obligatory better than other architectures, we have all the deep learning architectures. So if you have a deep learning task and you have image processing task and you have a deep network to solve, then maybe it's not the best idea to use neuromorphic chip for that. It's not built for that task. There are other hardware systems that probably solve this task better. However, if you have some other architectures, and many of them are some kind of recurrent neuronal networks, that could be lasso, right, in some sparse coding networks, some controllers, so SLAM, k-nearest neighbor search, graph search, constraint satisfaction problems that can be expressed as graphs. Those architectures sometimes run, 100,000 times less energy consumption than conventional compute, and also like 1,000 times faster. So really orders of magnitude better, faster. Okay, we have new fancy software framework, Lava, that allows you to both use deep learning if you would want to. You can deep train spiky neural network architectures, or you can build them just like as a designer, and then you can run them on different backends, CPU, GPU, or other neuromorphic systems, hopefully. And the last concluding slide. So I do believe that neuromorphic computing and AI have some joint future. Why? Because with the neuromorphic hardware, we can achieve power-efficient neuronal network computation, and that's important, right, to bring down our power consumption in this domain. We can build very diverse neuronal architecture, so it doesn't enforce particular structure and topology of your network. You can freely explore the algorithmic space that you have there. It could also be useful for neuroscience research, because you have some flexibility in models that you can run, and they can be larger scale. And you have this on-chip continual learning, big topic. And on the other hand, understanding how to properly program this neuromorphic hardware will require us to better understand how brains generate behavior actively. Without that, we cannot build these systems that will generate behavior autonomously. So it's reminding of the Feynman's saying that if I cannot build something, I don't understand it. So I can tell you today, we cannot really build this architecture. So I think we don't quite understand yet everything about how the brain controls behavior. So there's a lot of work for us to do, and these are good news, I guess. Thank you very much.